Hey guys, this is Mrs. Harbin, and we are going to continue with Pre-Cal Chapter 5. Today we are looking at Lesson 6, which is about the sum and difference identities. So we've been learning all of these different trig identities, and there are a lot. And so we're going to take a look at these two today and apply these identities to solving and proving other trig identities. Our life application for this unit continues to be that in order to understand and solve for the unknown, the student must build on a firm mathematical foundation. Just as in his daily life, he must seek to be a spiritual judge who subjects all things to the scriptures to discern what is right and wrong. We need identities. We need a firm foundation of things that are always true on which we can base our mathematical processes. And so many mathematicians accept that these mathematical identities are true because they've been proven time and time again, and have a harder time expecting or accepting spiritual truths. And we need to understand that spiritual truths are just like mathematical truths. They have been proven time and time again through life experience and the lives of different people, and that we need to base our decisions and base the next steps of our lives on these things that are absolutely true in His Word, and we can refer to the scriptures for those absolute truths. Our lesson objective for today is that you, the student, will evaluate trig functions using the sum and difference identities to prove trig identities from the sum and difference identities. So, remember this all the way back in Chapter 3. The cosine function is an even function. And what that means is that it's symmetric to the y-axis. So if you remember when I had you sketch the cosine function and sine function over and over, this is a very poor sketch here. Okay, the peak should be right there. The cosine function is symmetric to the y-axis. And what that means is that the cosine of any angle is going to be the same as the cosine of that negative angle. So cosine of, for example, pi over 3 is going to be equal to the cosine of negative pi over 3. So this is going to help us out when we're proving trig identities. If we see cosine of a negative angle, we can just swap it out, and change it to cosine of the positive angle, because cosine is an even function. Sine, however, let's write sine over here, sine is an odd function. Okay, it is symmetric with respect to the origin, and it looks something like this. This is a very poor sketch, okay? And what we know about odd functions is that the sine of a negative angle is equal to the negative sine of the positive angle, where before just the negative is equal to the positive. Now they're not equal, they're opposites, but we can make them equal if we put a negative sign in front of that angle there. That is going to help us with some of these identities that we are proving today. Dum, da, dum, da, dum. There we go. So let's talk about the fact that this is true. Cosine of x minus y is not equal to cosine x minus cosine y. Cosine is not a factor that we can distribute, right? So we can't just rewrite that as cosine x minus cosine y. So what can we do when we want to find the cosine of a difference of two angles, maybe pi over 3 minus pi over 6? If we want to know the cosine that exists between those two angles, well, we can use a couple of identities. And the proof for this is on page 252. And this is a kind of a very complicated proof. And sometimes you see the note here, as I say often, that it'll make more sense when we plug in values, when we're not just using x and y. But if we want to know the sum or the cosine or sine of an angle that's a difference of two different things, then we can use these sum and difference identities. I'm not going to go through this proof right now, but if you'd like to see the proof, you may look on page 252 here. All right, sorry, I had to take a quick pause there. I think a car alarm was going off outside in my parking lot. But 252 has the proofs for these. And on page 253, you can see the sum and difference identities for cosine and for sine. So cosine of x minus y, so the cosine of the difference of two angles, we can rewrite as cosine y, or cosine x, cosine y, plus sine x, sine y. The sum identity for cosine is cosine x cosine y minus sine x minus sine y. So notice for cosine, we've got opposite signs here when we rewrite that. The sine difference identity is sine x cosine y minus cosine x sine y. And sine of two angles, the sum identity for sine, is sine x cosine y plus cosine x sine y. So please notice here that when you're talking about your sine sum and difference identities, the operation symbol there, plus or minus, does match. So these are the 4 sum and difference identities that you need to be familiar with. So let's put some numbers in here and practice this. We want to find the cosine of pi over 12. So I'm going to rewrite pi over 12 as a difference of 2 angles because pi over 12 is not on my unit circle. So we're going to break this into values that we do know that are on the unit circle. And I know that pi over 12, which is 4 pi over 12 minus 3 pi over 12. If I simplify those two things, 4 pi over 12 simplifies to pi over 3. That's on the unit circle. And 3 pi over 12 simplifies to pi over 4. That's on the unit circle. So the first thing that I want to do is write pi over 12 as a difference of 2 angles that I know are on the unit circle. Then I'm going to apply the identity. So I'm going to use that little formula that we had on the previous screen. It was cosine of the first times cosine of the second plus sine of the first times sine of the second. So cosine pi over 3 times cosine pi over 4 plus sine pi over 3 sine pi over 4. Then I'll use the known values that I have from the unit circle. Cosine pi over 3 is 1/2 and cosine pi over 4 is root 2 over 2. So I'll multiply those two plus sine pi over 3 is root 3 over 2, and sine pi over 4 is root 2 over 2. So I'll multiply those two things together. When I do that, I get root 2, we missed a step here, root 2 over 4, and this becomes root 6 over 4. And then because I have a common denominator, I can add those here, and I get root 2 plus root 6 over 4. Okay, that cannot be simplified any further. Root 2 cannot be simplified. Root 6 cannot be simplified. And so that is our final answer. We can check this and verify that it's the same decimal value if we plug cosine pi over 12 into our calculator and we plug this into our calculator. You can verify that your answer is correct and that you will get the same decimal answer. All right. Remember that cofunctions of complementary angles are equal. And so there's a couple of notes that didn't get erased from a previous use here, but the cofunctions of complementary angles are equal. Remember that complementary angles add up to 90 degrees. So if we're talking about a right triangle, we know that this angle is a right or 90-degree angle. We know that our two other acute angles add up to 90 degrees. They are complementary. So if the measure of this angle is theta, then this one must be 90 degrees minus that angle, or 90 minus theta. So the cosine of an angle is equal to the sine of the other angle. So the cosine of this angle is equal to the sine of this angle, and vice versa. Those are cofunctions. Cofunctions of complementary angles are equal. You can see a list of cofunction identities on page 255, but here's an example for you. The sine of 5 pi over 12 is equal to the cosine of pi over 12. 5 pi over 12 plus 1 pi over 12, that's pi over 2. That's 90 degrees, so those two angles add up to 90 degrees. So the sine of one is equal to the cosine of the other. Okay, you can check that on your unit circle if you would like to verify that. A full list of cofunction identities is listed for you on page 255. So sine and cosine are cofunctions, tangent and cotangent are cofunctions, and secant and cosecant are cofunctions. So keeping that in mind, let's find sine of 5 pi over 12. The first thing we want to do, again, is break the fraction into values that we know. So 5 pi over 12 can be written as 2 pi over 12 plus 3 pi over 12. And both of those can be simplified to pi over 6 and pi over 4. Both of those are on the unit circle. So this is our first and this is our second term. We're then going to apply the identity, which says the sine of the first times the cosine of the second plus the cosine of the first times the sine of the second. So first and second terms here. Then we'll plug in the values from the unit circle that we know. The sine of pi over 6 is 1/2, and the cosine of pi over 4 is root 2 over 2. So we'll multiply those, and then we'll add the cosine of pi over 6 times sine pi over 4. So root 3 over 2 times root 2 over 2. When we multiply these, we get root 2 over 4. And we multiply these, we get root 6 over 4. And when we add those together, we get pi over 2 plus pi over 6 equals 4. Now, that may go, hey, we just saw that answer in the previous one. In the previous one, we were taking the cosine of pi over 12. Here, we're finding the sine of 5 pi over 12. These are complementary angles. They add up to 90 degrees. They add up to 6 pi over 12, which is just pi over 2, and pi over 2 is 90 degrees. So they are complementary angles, and these are cofunctions. The cofunctions of complementary angles are the same. That's why we got the same answer for both of those problems. All right, let's take a look at another problem here. If cosine x equals 5 over 13, and cosine y equals 4 over 5, where x is a first quadrant angle and y is in the fourth quadrant, evaluate sine x. So let's go ahead and evaluate sine x. Now, to do this, I'm going to draw a little right triangle here to help you kind of imagine what we're doing. So this is triangle x, okay? So here's angle x. And we know the cosine of x is 5 over 13. Remember that cosine is just the ratio between adjacent over hypotenuse. So the adjacent side is 5, and the hypotenuse is 13. And we want to evaluate sine x. So we're trying to find the opposite side over 13. Well, we could use the Pythagorean theorem here. Could we not, to find our missing side? We could say that 5 squared plus whatever this other side is. I'll do an S for side. Side squared equals 13 squared. And we get 25 plus side squared equals 169. And if we continue from there, we can find out what our side is. And you'll find out that your side is actually 12. And we didn't want to know just the side. We wanted to know the sine. And the sine is a ratio between opposite and the hypotenuse. So our sine x would actually be 12 over 13. Now, that's probably the easier way to do that, but you could also use the Pythagorean identity, which is pretty much exactly the same thing. It just uses fractions here. Cosine squared x plus sine squared x equals 1. Cosine squared x, cosine is 5 over 13, so cosine squared is 25 over 169. And we then subtract 25 over 169 from both sides and take the square root, and we get 12 over 13. So either way, drawing a triangle and solving for the missing side before writing your ratio, or just using the Pythagorean trig identity, either one of those will work. All right, let's go ahead and evaluate sine y. Again, we can do it using the Pythagorean identity, or we can use a little triangle here. I'm going to make this angle y, and we're told that cosine y is 4 over 5, so adjacent over hypotenuse. We just need to find this missing side so that we can write the sine y. Now, I can do this one pretty quickly here because this is a special triangle. If one leg is 4 and the hypotenuse is 5, I know the missing leg is 3. However, we're told that this is in the fourth quadrant. And in the fourth quadrant, my sine values are down here. So my sine values are all negative. So this is actually a negative 3. So my sine is negative 3 over 5. Using the Pythagorean identity, With fractions, I get 16 over 25 plus sine squared y equals 1.